the chart. Acid-base equilibrium. This is our last section. We're going to do this real quick. Acid-base equilibrium has to do with absorbing things. And when we talk about equilibrium, we're talking about this two-way street right here, okay? The two-way road. We'll talk about it in a second. In an equilibrium reaction, remember when we wrote this like this, right? With a two-headed arrow here. Oops. Now, because it's got a two-headed arrow, you can take this and break it up into two reactions. One going forward and one going backward, really, right? So we have our forward reaction and we have our backwards reaction. If we write both of them as going forward, right, all we've done is we've taken that reverse one and flipped it around and written it going forward, okay? Look, these guys over here are these guys down here, right? Mm-hmm. And these guys here are these guys here, right? We just reverse the reaction. So a forward reaction and a reverse reaction, okay? Anytime you see the arrows like that, two-headed arrows, it means the reaction go forward or reverse. You can write in either direction. Now, what happens? When the forward reaction, how fast the forward reaction is occurring equals how fast the reverse reaction is occurring, we say that we have reached an equilibrium. What it really means is that the concentration of the reactants is not changing anymore, and the concentration of the products is not changing anymore. So if we start with all reactants, we're going to make some product, right? Well, when that means the concentration of reactants is going to go down, the concentration of products will come up. At some point in time, the two will stop changing concentrations. Look right here. After this point right here, look at this is concentration on this axis, right? Look at these concentrations over here. Are they changing anymore?
No.
No. Now, what's a little bit weird on here is that the concentrations don't have to change by this much. I'm going to redraw this graph. I might have a reaction that looks like this. Has this reaction reached equilibrium?
Yes.
Yes, it has. Even though my reactant concentration didn't go down very much, and my product concentration only came up a little bit, they're no longer, those are supposed to be flat lines out there. They're still not changing anymore. Now, it doesn't mean nothing is happening. What's happening is reactants are going to make products, and products are going to make reactants, but that rate is the exact same. It's like if you put water in a bucket, and the bucket's full, what happens to the water? It overflows. Well, how much water overflows? The same amount that you're putting in, right? So it's going back and forth really rapidly, right? It's not like nothing's happening. Okay? Same thing here. It's not like I'm not making more products, but for every time I make one product, what happens? Products go back to be reactants. So it's like, let's say we go out to the street out there, and I put 10 people on each side of the street. And I send somebody over to one side, to the other side. Well, if we're at equilibrium, every time I send somebody to one side, someone from the other side has to come back at the same time. Okay? The two have to be exactly the same. The rate at which they're happening is exactly the same, and that way concentrations won't change anymore. Now, we're not going to work on this. Okay. When we alter the concentrations of things in an equilibrium reaction, the reaction will respond. Okay? And this is called Le Chatelier's principle. Le Chatelier's principle states then when a reaction is at equilibrium, if you perturb it, change it, it will react such as to relieve that stress that occurs, okay? How do we react to relieve stress? That's what we got to decide. The Chatelier's principle tells us. Let's look at this reaction. This is not a reaction, but an example. Here we have two water tanks connected with a thing in between. If we add water to tank A, what happens? The level in tank A goes down and the level in tank B goes up, and we get a new equilibrium established. Okay? So let's think about that in terms of a reaction. If I add some reactants, what's going to happen? It's going to make the reaction go over here. Fair enough? But watch this. I can also add something over here. What's going to happen? It'll make the reaction come this way. Okay? So if I add reactants, it makes it go towards the products. If I add products, it makes it come towards the reactants. Okay? You can also remove things. What if I remove some product? What do you think will happen? If I remove product, it makes it come this way. If I remove reactant, it makes it come back this way. Okay? We talk about each one of them. Now, think about what happens in your body and your blood. Let's talk about your blood. As it goes into your lungs. Does your blood have a lot of oxygen in it when it gets to your lungs?
No.
No, it does not. But where is there a lot of oxygen? In the air in your lungs, right? So here we have blood with no oxygen, and here we have air with lots of oxygen. What do you think is going to happen? It's going to transfer, right? Got to have that equilibrium reestablished. It transfers the oxygen into the blood. Now, when that blood gets out to your cells in your body, what happens? Cells in your body have how much oxygen in them? None. Why not? Because they use it, right? But your blood has high oxygen. What happens? Transfers it. Make sense? Your blood loses oxygen, your cells pick up oxygen. Now the opposite reaction is also occurring, right? What do your cells have a lot of? What gas do they have a lot of? Carbon dioxide. What does your blood not have a whole lot of? Carbon dioxide. So what happens? The cells lose carbon dioxide and the blood gains it because there's an equilibrium trying to be established here between the two, right? That equilibrium says high concentration, transfer, make it go over to the low. So CO2 goes one way, oxygen goes back the other way. And that's how your blood works. This is hemoglobin, right? It's a two-way street. When your blood gets to a place where there's no oxygen, so this is in your cell, no oxygen, what do you have? Here comes your blood from your lungs, lots of oxygen, and it gets to a place where there's no oxygen, what happens? Makes it go this way. Okay? In your lungs, what happens? There's lots of hemoglobin and there's lots of oxygen in your blood or in your lungs, so it makes it go that way in your lungs. Forces you to make hemoglobin oxygen, right? The complex. When it gets to the cells, it drives it back the other way and you release the oxygen for the cell to use. Does that make sense a little bit? So it's driving this back and forth, and that's how your blood transports oxygen around and how it gains and loses oxygen based upon concentration changes. I care about that. And on next Monday, we will talk about the dissociation of water. Why are we not going to do that Wednesday? We're going to have a little question and answer period on Wednesday. See you guys then.
So we need a
Yeah. That's copper 2 hydroxide.
It's a base.
It is a base. Anytime you see the hydroxide, it's going to be a base. In this case, it's a weak base, right? Copper hydroxide is a weak base. I just do. I'm not going to ask you to know that. Okay? All right. I'm not going to worry about this either.